Hey there, classmate. Look, if you're feeling a little overwhelmed by the sheer mountain of stuff we've got to memorize for this upcoming computer science exam, take a deep breath. You are in the right place. Today, we're going to absolutely ace this test by decoding computer memory and storage from the inside out. I actually put this explainer together to be your ultimate study guide, so grab your notebook and let's make sense of how our machines literally hold on to all that digital information. So, here is the game plan for today's explainer. We're going to cover 1. Memory versus storage. 2. Primary memory, RAM and ROM. 3. Hard drives and magnetic storage. 4. The solid-state solution. And finally, 5. Reading optical media. Let's dive right in. All right, Section 1. Memory versus storage. To keep your exam notes perfectly organized, I highly recommend drawing up a quick 2-column comparison chart for this concept. Okay. To really wrap our heads around this division, I want you to think of primary memory exactly like the top of your physical school desk. It's your immediate workspace, right? You can grab your textbooks, your pens, whatever you need instantly. But it has one massive flaw. It's volatile. Volatile memory forgets absolutely everything the second the computer loses power. Imagine someone just running by and sweeping everything off your desk the moment you blink. That's volatile memory. Because of that, we desperately need a separate long-term filing cabinet to permanently save our hard work. And that filing cabinet is what we call secondary storage. Moving right along to Section 2, primary memory, specifically RAM and ROM. Let's introduce the first star of our motherboard. This is a RAM stick, which stands for Random Access Memory. Now, you might also see it called the Immediate Access Store in our textbook, so definitely jot that down. It essentially holds the data, files, and programs that the CPU is using right this exact second. The read and write operations here are incredibly fast, so when you open, say, a dozen browser tabs or fire up a really heavy video game, all that active data gets loaded right here into RAM so the processor doesn't have to wait around for it.
Now, we've got to contrast RAM with its sibling, ROM, or read-only memory. So while RAM is your super-fast, temporary, volatile workspace that you can constantly read from and write to, ROM is a whole different beast. It is non-volatile, which means it's permanent. It actually holds the absolutely crucial startup instructions, the BIOS, that tell your computer how to basically wake up when you hit the power button. And like the name implies, you can't write over ROM, it is strictly read-only. Honestly, that's a guaranteed exam question right there, so make sure you highlight that distinction.
Which brings us to Section 3, hard drives and magnetic storage. Because RAM is volatile and completely amnesiac when the power drops, we need that secondary storage for long-term preservation. Let's start with the trusty hard disk drive.
The crucial thing to understand here is how an HDD actually organizes your data. Inside that heavy metal casing, your files are stored magnetically on these spinning disks called platters. Think of a platter like an old-school vinyl record. The surface is perfectly organized into circular rings called tracks. Then, imagine cutting that track up like slices of a pizza. Those slices are called sectors, and each one holds a fixed number of bytes. The computer basically uses a tiny electromagnetic read-write head on a mechanical arm to magnetize those specific sectors, saving your data permanently.
But here's the catch, and it's a big one. It's a physical limitation known as latency. Latency is this agonizing delay caused by waiting for that spinning platter to physically rotate the correct sector until it lines up perfectly with the mechanical arm. Because it relies on actual moving physical parts, an HDD is always going to be vastly slower than the lightning-fast electronic speeds of your CPU or your RAM.
So, how in the world do we solve the physical limitations and that annoying latency of spinning magnetic disks? Welcome to Section 4, the solid-state solution.
SSDs completely obliterate latency because they have absolutely zero moving parts. None. This makes them infinitely faster, incredibly energy efficient, cooler, and so much lighter. If you've ever wondered why modern smartphones or super thin laptops have batteries that somehow last all day, it's totally because they use solid-state technology instead of those bulky, power-hungry spinning hard drives.
So how do they work without magnetism? Well, SSDs use millions of microscopic transistors called NAND gates. Think of it kind of like a microscopic maze. Electrons flow in from a source and they get pushed into these things called floating and control gates. Once they are forced in there, boom, they're trapped. And by trapping those electrons, the drive creates permanent, non-volatile binary ones and zeros. Even when you're completely shut down your laptop, those electrons stay locked in those gates, keeping your photos, your apps, and your final essays perfectly safe.
Now, while solid-state tech, like what's inside your everyday USB thumb drive, relies on those tiny electronic chips, optical media uses a completely different physical mechanism to store files offline. We're transitioning from the microscopic transistors of an SSD to the shiny reflective surface of an optical disc.
And that brings us to Section 5, Reading Optical Media. Let's look at CDs, DVDs, and Blu-ray discs and find out exactly how lasers read their secrets. What's really wild about optical mechanics is the track layout itself. Unlike the separate concentric rings on a hard drive that we talked about earlier, optical discs use a single, continuous spiral track. It literally runs all the way from the very center of the disk straight out to the edge. And to read the data packed onto that tight spiral, the drive focuses a highly specific wavelength of laser light right onto the spinning surface. But how does a beam of light actually become data? Well, the surface of that spiral track isn't perfectly smooth. It's actually covered in these microscopic bumps called pits and flat areas called lands. As the disk spins around, a laser is fired at the track. When the laser hits a flat land, the light reflects cleanly back into a sensor, and the computer reads that as a binary 1. But when it hits a bumpy pit, the light scatters everywhere, and the sensor reads a 0. Just by reading tiny reflections, your computer is decoding a massive binary sequence. Pretty cool, right?
Let's quickly summarize this for your exam notes. A CDR is a write-once disk. You use a laser to physically burn the data into a layer of dye, and once it's there, it can never be changed. A CDRW, on the other hand, uses a special material that lets you rewrite it multiple times. And if you're looking for massive storage capacity, you go with Blu-ray. Blu-rays use a specialized blue laser with a much shorter wavelength than standard red lasers, which basically means they can read pits and lands that are packed unbelievably close together.
But physical discs aren't flawless, are they? Have you ever popped in your favorite movie or an old game disc only to have it randomly glitch out, skip, or just completely refuse to read?
The culprit is often hidden right beneath the surface. You see, to cram more data onto standard DVDs, manufacturers use this trick called dual layering. They stack 2 recording layers on top of each other, separated by this little transparent spacer. That means the laser actually has to read the second layer through the first one. This complex light bending can sometimes cause refraction errors, which is a fancy term called birefringence, where the laser just gets completely confused. Add in the fact that everyday physical scratches on the disk can permanently destroy those tiny pits and lands, and you've got a recipe for permanent data loss. So definitely write down highly susceptible to physical damage as a key disadvantage in your notes.
As we wrap up this explainer, I want you to think about where all this technology is actually heading. With cloud storage holding our files remotely on massive servers and software virtual memory seamlessly backing up our RAM when it gets too full, it begs a really fascinating question to leave you with. As internet speeds skyrocket and SSDs get even more microscopic, is physical secondary storage going to disappear from our personal devices entirely? Good luck on the exam, classmate. Study those notes, remember the desk versus the filing cabinet, and I will catch you in the next explainer.